Alright, so when you get smaller and smaller and you start picking apart atoms and looking at the subatomic particles, at some point you have to deal with what's called quantum mechanics, which I'm sure you've all heard of, but you probably have very little idea of what the hell it means. But the modern version of quantum mechanics, what it grew into, is called quantum field theory. And I'm mostly going to just give a brief overview of that form of quantum mechanics, which is the most up-to-date form it has. So quantum field theory is, so first, when you break apart particles, there's composite particles and then there's elementary or fundamental particles. So you think like the proton, as Sean talked about earlier, breaks into 3 quarks. But the quarks are fundamentally different than the proton, and that the proton has a volume, it takes up some size, and you can't squish it below a certain size, and it's made up of something else, whereas the quarks, we assume, are elementary, and they're represented, well, they're first represented as point particles, because no matter how far you try and squish them, you can localize them to as small a space as you want. They don't appear to take up any size. But on the other hand, now with quantum field theory, we view these particles not as these points moving around really, but as excitations of quantum fields. So these quantum fields, each particle has a quantum field that fills all of space-time, and it's ripples or waves on the quantum fields that look like these particles, except that the waves, a classical wave is just like you'd see in the ocean, but these waves are quantized. That's where the quant in quantum comes from. It's quantization. Like instead of being a continuous quantity, like if you were to take a liquid or something, it seems like, well, you keep breaking it up and it seems continuous. But if you have a discrete number of things, you can count them. So these waves, they can only happen in certain excitations. You can pump a little bit of energy into the quantum fields and it generates one particle, and you can pump a little bit more energy and it generates another particle. But by particle, we no longer really mean like a little ball moving around. It means an excitation of a quantum field. And that was kind of a radical departure from the previous way of looking at it. Although, to tell you the truth, in physics, it gets really tough to say what exactly we're talking about, because there's all sorts of things called dualities. Like you may have heard of wave-particle duality. You can talk about it as if it's a particle, or you can talk about it as if it's a wave. It has both of those aspects to it. There's sort of a duality between the two. We'll talk a lot more about dualities later. And so whether it's fields or particles or waves or strings, we're talking about the same thing. It's kind of different ways of getting a handle on what's going on. So in quantum field theory, we represent interactions between particles scattering off of each other by what's called thanks, Sean, by a Feynman diagram, which is, ignore this diagram here. This one on the left is an electron. This is an electron, and we should have drawn the time axis would go up here. So this is time and this is space. And the electron's going along, and then all of a sudden it emits this wiggly little thing, which is a photon. The photon is the quantum of light. So the electron exchanges forces with other electrons based on light, or more generally, we think of visible light as stuff you can see, but there's the whole electromagnetic spectrum, like radio waves and X-rays, and that's all responsible for the electromagnetic force. So the photon is the quantum of the electromagnetic force. It can emit one like this as it's going forwards in time. But an interesting thing is there's a theorem in quantum field theory which says that if you've got space on the bottom here and time going up, you can always rotate the diagram, interchanging space and time, and all of a sudden you still have a valid interaction between particles. And so now there's a name for an electron that looks like it's traveling backwards in time. If this arrow, instead of going with time, like this would be an electron, if it's going against time, then we call it a positron, which is basically the antiparticle. So each particle has an antiparticle, and this was predicted as a prediction in quantum field theory. And I think it was pretty amazing that they predicted this just from pure theory, and then it turned out then they discovered all these antiparticles in the accelerators. And so now we can actually produce antimatter in somewhat large quantities, but it's known to be a real phenomenon now, not just a theoretical. Some of the things we'll get to later will be entirely theoretical, but so once you have these, so we have matter and antimatter, and this actually gets into a brief note on what Sean and I have actually been working on. We just published a paper on was the origin of what's called the baryon asymmetry, or matter and antimatter asymmetry, which is that there appears to be a whole lot more matter in the universe than antimatter. I mean, if you look around you, everything's made out of matter. And in fact, one of the properties of antimatter is if it comes into contact with regular matter, if two particles of the same type, like an electron and an anti-electron or a positron, they would annihilate in a flash of light. In fact, that diagram I meant to say, when it's turned that way, it's actually an annihilation diagram. So you've got the electron and positron coming together and then just annihilating. Then all that's there is the photon or the light. So it's matter turning into pure energy. And this has even been proposed as a weapon. It would be probably the most efficient bomb you could have because it releases all the energy. So an antimatter bomb. I think the U.S. government is actually looking into this, but
that's not why we study physics.
That's not our motivations, but it's a powerful thing. So beyond the standard model, so the standard model that Sean discussed, and which is written kind of in the language of these quantum fields, quantum field theory, it's the best tested theory we have that accounts for all the different observations that physicists have made in these accelerators in outer space. But we have certain hints that things go beyond the standard model. One of the biggest is dark matter, which actually has been talked about for a while, but just last week NASA announced that they found the first real direct evidence of dark matter, which is pretty exciting. And that's another thing that was related to our work that we just did. So dark matter is matter that we can see in distant galaxies, and we notice its gravitational effects, but we actually can't see the light from it because it must be some kind of particle that doesn't give off light. We don't know what it is, but we know it's not one of the particles in the standard model. It's something else very mysterious, and so that's why it's called dark matter. But we know it's out there. We know it exists. So next, I guess Sean's gonna go forth with a little bit of general relativity.